Today we are going to look at the discrete Fourier transform. Now, previously we described input-output characterization for a discrete time system in the time domain, and we saw that it could be described using the convolution sum. So we looked at that last week, and we saw how the convolution sum is calculated. Now, so far we have been doing everything basically in the time domain. In other words, we are working on discrete time samples. We're defining our system in discrete time as a sequence of discrete time values. Sorry. And of course the output in discrete time sequences as well. But there are a lot of problems in dealing with things in the time domain. Sorry. But one. Right, but fortunately we can look now at doing things in alternative domains. In other words, we're going to look today at looking at things in the frequency domain. And if you're not too sure, I will explain a bit more as we go along. So time domain is all very well, but it is tedious, it is hard. It's like trying to do maths without your calculator, or in the old days, we had to use log tables, trying to do a lot of mathematical problems without our log tables, slide rule, or calculator later on. So the first perhaps the most common domain really is to look in the frequency domain. And you would already have been familiar with this domain, having done the Fourier transform in the continuous time. Now we have to look at Fourier transform in the discrete time. Fortunately, much easier to do. MATLAB will do it for you. MATLAB will do everything for you, but you need to understand the theory and how things are done. So that's what we're going to do today. We're going to start looking at the Fourier transforms. And when I say start, it's because we'll see that there is more than one form of Fourier transform in the Fourier transform, leave it at that, in DSP. In fact, I will mention there are three possible. They're all based really on the same principle and the same thing, but the one we're looking at today is the discrete time Fourier transform, and then there is a discrete Fourier transform, and then a very fast algorithm, which is a fast Fourier transform, which we won't actually learn to use, but if you understand the Fourier transform in general, then it's very easy. If you have to go and learn the fast Fourier transform, very easy to understand and do. So today we'll do the discrete time Fourier transform, and then maybe not next week, but pretty soon we'll just do the discrete Fourier transform. I'll explain again the difference before we finish today. Right. So you can define then a system in the time domain as a sequence of numbers. FIR systems have a finite impulse response, that is a finite number of values in representing that system. Infinite impulse response system, of course, will have an infinite sequence representing the system. But we showed last week that you can still represent it in a closed form because you have your feed forward paths and your feedback paths. And as we go on more, it will become more easy to understand and deal with. But we then know that we have a sequence representing a system. Now, especially for those who are audiophiles and they like their music and their power amplifiers and their equalizers and so on, you will be aware that and many other areas in life here, we know that we sometimes easier to talk about a frequency, things in the frequency domain. What is the response of your amplifier? Is it from 40 hertz up till 15,000 hertz? Not a very good system for those audiophiles. What about from 20 hertz to 20 kilohertz? So we would be familiar then with how we discuss our systems in the frequency domain. That is talking about it in the frequency domain. So now we are considering an alternative description of a system sequence. And this will be in the terms of complex exponential sequences of the form e to the minus j omega n, right? And in following lectures, we will look at the complex variable z to the minus n. So this is the z transform, as I am sure you're already introduced to.
Pardon, sir. Can you check the waiting room, please?
Okay. Right, thank you. Seeing it come up to 5 minutes. Oh, really? Why am not? I am not seeing the thing to say admit them. Can anybody help with this? I'm not able to admit them. I'm seeing where.
Sir, why don't you just turn off the waiting room completely?
All right. Tell me how I do that. I am more with that. How do I turn off the waiting room?
So I think there's an area at the bottom that says security. Do you see?
All right. Security, lock meeting, hide approach.
You see it?
Yeah, I'm in security now. Hello.
And you took off the check mark that was on lock meeting, yeah?
You have locked the meeting, no one else can join. I think it was off. No, okay.
Oh, wait,
I have unlocked the meeting, new participants can join. Okay. Well, I'm hoping they can join, but I'm not seeing where it says admit them.
No, as in in terms of specifically waiting room. On that same security tab in the top right corner, there's like a little I don't even know how to describe that. There's a little it's like a
more?
I don't even know what to say. Yeah.
More?
Not really more, but
no, I'm looking under more.
No, on the same security tab.
I am not seeing.
Hold on.
Yeah, take back up.
Transfer host to me for a second, please. No, wait, never mind. It's gonna stop the recording if you do that.
I would like to pause recording. I'm going to pause recording anyway.
Hold on 1 second, sir.
Oh. All right. Hello. Hi.
Yes, sir, we're here now.
Right. I saw it come up all of a sudden. So I admitted them and then they're on now. Can I continue now?
Yes, sir.
All right. I'm gonna start resume recording. Now.
You took off the waiting room, sir?
Yes, they're all in now that I can see. Right, so I'm going to resume recording now. So, continuing regarding the frequency domain representation of systems, we know commonly that one frequency domain representation that we use quite frequently in normal life is to talk about the frequency response of our system. So first transform domain that we examine is a discrete-time Fourier transform, which we'll go through today. And the time domain sequence that we're familiar with is then mapped to a continuous function of a frequency variable. Of course, the frequency variable is either in hertz, which is a plain cycles per second, of course, or it may be in radians per second. Okay, so that's 2 pi f. 2 pi f gives us our, if we know our frequency, then our radian frequency is 2 pi f. Now, the discrete-time Fourier transform then is simply the Fourier transform of a discrete-time sequence. Now, the DTFT, where it exists, is unique and invertible. In other words, if we take the discrete-time Fourier transform of a sequence, it produces a unique output, which may be complex. Well, most of the time, it is a complex sequence. And it is also invertible. That means you can take a sequence which has been transformed and reconstruct the original sequence in the discrete time. It is invertible. So we come then to what is this transform? And here is the transform. Our, our sequence in the time domain, or not in this case here, we don't get a sequence for this, we get a continuous function. But our transform signal then of a sequence x of n is defined by this. It is very simple. Here's our x of n. Remember, x of n is simply a sequence of numbers, and then it is multiplied by this function here, e to minus j omega n, where omega is a frequency, right? and our output here is a complex function of the real variable omega. So being a complex function, then we can represent it as a real component and as an imaginary component. From this real and imaginary, from the real and imaginary components, then we can get a magnitude and a phase. Remember now, the magnitude will be the real value plus squared plus the imaginary value squared, and we take the square root of that. All right. We can also get our phase. So when we have a signal, it might be shifted in phase, and therefore this component here is telling us the phase, and this component is telling us the magnitude. So it's all there at the bottom. Right, and that's about it. So the best thing now is to look at an example. So here's our example. Here's a fairly simple system with a difference equation shown below. So here's our output, y of n, and these are our input values here. Our input is x of n, and these are our coefficients of our system. So I should really have included a little diagram of what that system looks like, but anyway. So we want to determine the frequency response. So again, we're going to use this very useful identity. If x of n, that's our input signal, is equal to delta n, that is our impulse function, then our output y of n is equal to our system response h of n. And so given this relationship here, then we can now express this difference equation in terms of h. So our h of n then is equal to quarter delta n plus half delta n. Sorry, okay, so something missing there. Sorry, this should read, then h of n is equal to quarter delta n plus half delta n minus 1 plus a quarter delta n minus 2. Very important omission there. I will correct it, and I will send it out corrected. Therefore, right, so h of n then is equal to this sequence here, where this is our zeroth value, and this is 1 and 2. Right, so n is less than 3 or equal and less than 2. Right, so using the DTFT then, our limits are from 0 to 2. Our sequence is h of n, and our transform is as shown here, e to the minus j omega n. So we plug in the values. So we can say then that, right, this is saying the same thing again. So plugging in the values then, we have here h of 0 is a quarter, e to the minus j, so n is 0, so a quarter e to the minus j 0 omega, that is the first term. Okay, when n is 1, then our term is half e to the minus j 1 times omega, and when n is 2, then our term is quarter e to the minus j 2 omega. Just simple, just plugging in the values for h of n, that's quarter, half, quarter, and in here we're plugging in the values for n, 0,
Sir.
1, and 2. Yes?
Some people are asking to be let in.
The Latin, okay, all right.
Yeah. You say you turned off the waiting room?
I'll check.
On that same security tab, when you click on it, you're at the top, the second thing should say enable waiting room. You see that?
Yeah, and it's ticked.
Does it have a tick beside it?
Yes, yeah, that's tick beside
Press it.
Also,
you press
not
it, sir?
bright. It's not bright, so I don't seem to be able to change it.
No, as in once you click it, it should say disabled waiting room.
No, as I say, lock meeting is bright, hide profile pictures is bright.
Oh, as in it's not highlighted.
Enable is not bright. It's not. Doesn't look like I can change it.
All right, sir.
So, but it does say enable waiting room. Are you wanting to change that?
Yes, sir. Uncheck it.
No, that's what he's saying. It's not giving him the option to do it. Like it's sure it's not what do you call it? It's dim. It's dim.
Yeah, it's dim, right. It's ticked.
All right, next time we start the class, we'll fix that.
Okay.
But for now, you can let in the persons in the waiting room. So.
I think I've let them all in. I don't see any more waiting now. Right, so I'll continue. Right, so we have plugged in the values for, here are our coefficients, quarter, half, quarter, and then here our values of n going from 0 to 2, 0, 1, and 2. All right, so next line then. All right, so clearly then e to the minus j0 is going to be 1. So our first term here is quarter, half e to the minus j omega, quarter e to the minus j2 omega. Now, from this expression, we can obtain the magnitude and phase at any frequency omega, just by plugging in the frequency. And remember, it will be a radiant frequency, so it will be, it will be a function of pi. And plugging it in and doing the calculation then can give us our response at any frequency. I'm sure you're aware that E, all right, for example, e to the j omega is cos omega plus j sine omega, right? So it can be expanded into a real and an imaginary term. So each of these can be expanded. We can get the value and we can calculate what our response is. We may also, in some cases, be able to do a sufficient plot as we show here now. So we take these two terms here with quarter and we bring them outside of our bracket. So we have here quarter into 1, that's quarter, and quarter e to the minus j2 omega, that term. And then we have this other term here, which is outside. Right, now if we multiply what's in the bracket here by e to the j omega over e to the j omega, remember this is 1, so we're not changing anything, we're just multiplying this bracket out. we repeat it here again for convenience. So what will happen is that this e to the j omega term will come here. Multiplying that by that will leave us with e to the minus j omega, and the 2 from this quarter here will come inside. So inside the bracket we get this term here, and we're left outside with 1 over 2 e to the j omega. In other words, this term here comes over here. Now, this term here is just simply cos omega. So, I just gave you back the same, basically the same equation, but bringing e to the j omega from the bottom to the top now makes it e to the minus j omega. So we have here the same term as that, really. So what we can do now is that we can make it all very simple. We can bring the half e to the half e to the j omega. It's still outside. Half we bring to the front because it's really multiplying this term here and then times e to the minus j omega there. And what we should recognize now here is that this is purely a real term. Half cos omega plus 1 is a real term. It is a magnitude. So this here is the magnitude term of our system. And this,
sir,
yes, more.
Shouldn't that cos be cosh? Cosh omega instead of cos omega?
Not as I remember. I remember cos omega is this over 2, and sine omega is e to the j omega minus, is it e to the minus j omega over 2j. So if you look it up anyway, good exercise, look it up. It should be cos this term inside.
Yes, sir.
And maybe I shouldn't have I don't know why the capital C came in there. Anyway, this term here is a real term, gives you a number. Any value of omega you put in there, it will give you a real number. And this here is the imaginary number. So this here is the magnitude here, and this here is the phase. So what we can do is that we can, to get an idea of the frequency response of the system, let's evaluate this at a number of values of omega. Now, right, here we're saying, putting in this note, which we should have had a lot earlier. So let's take the first case then, when omega equals 0. In other words, 0 hertz, DC, whatever you want to call it, right? So here, if we put omega equals 0 into this equation here, we have cos of 0 is 1. So 1 plus 1 is 2. A half is outside. So 2 over 2 gives you 1. A gain of 1. Here, our phase angle is 0, as shown there. So at DC, our system here passes the signal through without any attenuation. So what goes in comes out in terms of amplitude, and the no phase shift. Right, so we can move a little way around. Angle when omega is equal to pi over 3 radians, then our equation, if we plug pi over 3 into here, we get and work it all out. So I think we get 0.5, and 1.5 over 2 is 0.75. So we get our gain of, gain of 0.75. In other words, or is actually attenuation. So our signal begins to be attenuated, and at that frequency, that is the attenuation. Or in dBs, because we will have to be familiar with dBs. I hope if you're not, we can probably try and do a little tutorial on it. But in terms of decibels, and it's very convenient because it has a wide dynamic range. So if something has a gain of 100 down to minus 100, we can represent it in a much more compact form in terms of decibel. And our angle e to the j omega, notice is minus 60 degrees, because here we see that we have a negative in front of our angle here. Right, so that is the next point. And then we come now to omega equal pi over 2 radians. Right? And that is half of the frequency you would normally be expecting to pass. And here now you have, when you plug pi over 2 into cos, that is cos 90, I think is 0. So you just have the other one inside that bracket over 2. So the gain is 0.5 or minus 6 dB, and so on. And then I think we'll do 2 more. This one, 2 pi over 3, we get gain of 0.25. So what we're seeing is that we started with a gain of 1, and then it's coming down 0.75, 0.5, 0.25. And then the last one now, when omega is equal to pi radians, then our gain is 0. In other words, no signal is passing through. And with our phase shift at that point would be minus 180 degrees. Right, so if you're able to follow it very well, clearly then what we have is a low pass filter. We have a filter which allows all the signals through at 0 hertz, and then as frequency goes up, we end up having a lower and lower gain until at pi radians, then the gain is 0. So here I think originally for my notes, I had done a sketch. So this is not a very good diagram, but it's basically showing, our signal going down from 0, 0.25, 0.5, 0.75, 1. So this is what our gain would look like as we go from 0 hertz up through pi hertz, which is half the sampling frequency. And here we see our phase, which is changing linearly. So at At 0 hertz or 0 radians, there's no change in phase, but it changes linearly as we increase in frequency. But I only put that in. I will show you now how we would do it in MATLAB. So in MATLAB now, you can confirm it as follows. Here, you're simply going to define what your system is. So H is equal to 0.25, 0.5, 0.25. It's only 3 coefficients. Right? It's confirmed here. And then in MATLAB, you can do a frequency plot. And so you simply type FREQZH, and you're given the frequency plot. Now, actually, I should have done one without modifying anything. Okay. Here, though, we're seeing our frequency, normalized frequency in radians per sample. And I will say a bit about that in a little while. Here we're seeing our magnitude in dB. Now, I used to remember how to give it in terms of gain, but I was running out of time putting it in this afternoon. So it's in dB. Now, here now is your minus 3 dB point, minus 2.997, approximately 3 dB, minus 3 dB. This is your half power point for your filter. In other words, it is the cutoff frequency of your filter. Right? So although this plot here looks very different from the one I drew, it's because I drew that one in terms of gain, whereas this is ordinary gain, whereas this one is in terms of dB. Here, though, we see our phase is a straight line and decreasing or changing negatively. As the frequency increases, your phase shifts in a negative direction, as we saw from our previous equation. Couple of things. I don't want to throw too much at you at one time, but notice here that our phase changes linearly. These filters are known as linear phase filters. Think I am generally, I will say generally, FIR filters are all going to be linear phase. That is finite impulse response filters. Those are the filters that only have your feed forward paths, right? The filters that have feedback paths are not going to have linear phase. I think there is a certain formation of components that can give you a linear phase, but for FIR, but definitely FIR filters are linear phase. And for many reasons, this is very desirable in the electronics world to have a linear phase change. But that's by the way, really. Here, I expanded the filter response a bit, because remember we said that our 3 dB point was somewhere about here. Now I'm showing a minus 12 dB point here. And why I did that is because if I go back, go back to this point here, we will find, and I didn't put it in, that this value here, 0.25, is minus 12 dB. I put in a minus 6. I think I put in a minus 3. Well, this is minus 2.5. put in -6 and I failed to put in -12. Anyway, if you take 20, it's 20 log of 0.25, you should get -12. And that is the -12 dB point here. So I just did it here to show that it's 0.67667 or 2/3 pi. Notice that this is normalized to pi radians per second. So this means 2/3 pi. Right. All right. Now, there's a lot that I have said that may cause some confusion. I really do apologize for not going through analog to digital conversion, or as we would say in DSP, continuous time to discrete time conversion. I know some have done it in communication, digital communication. Am I right? Or you're doing it, or in communication theory? I'm not sure. You will have to give me the feedback on that. But some may not have done it. So I had every intention to start today by going through continuous time to discrete time conversion. Unfortunately, it didn't work out. So I would like to explain a few things. First of all, you're probably saying, well, I don't know anything about this pi radians per sample. What does it all mean? I hope I am just going to explain it off the cuff. Now, everybody is familiar with frequency in terms of hertz or cycles per second, as it used to be known, hertz as it is now known. For example, I'm sure everybody knows that your main frequency in Jamaica is 50 hertz, that your voice frequencies are somewhere between 100 and not very high actually. It's maybe at the most 7,000-8,000 hertz. I don't know if a human voice can go higher than that. So you're familiar with frequency in terms of hertz. Now, in digital signal processing, you have the continuous time signal has to be converted to a discrete time signal. Computers cannot deal with continuous time, either amplitude or time. It cannot deal with it because there are infinite number of values when you're looking at continuous time. There's an infinite number of values when you're talking about amplitude, amongst other things that have infinite numbers of values. So, signals which are continuous in time and amplitude, continuous time signals, have to be converted, which is the analog to digital or the sampling process. So it means that we have to sample our signal and convert it, our continuous time signal, and convert it to digital discrete time and discrete amplitude. For now, we don't need to worry about the discrete amplitude part of it. We'll talk more about that as we go along. But in this course, really, we don't really consider too much the discretization or the quantization of your amplitudes. So we'll more concentrate on discretization of your times, right? So you have to choose a number of times that you sample your signal per second. What was found out by Hartley was one, and oh dear, a famous, the greatest man in digital, but I've forgotten his name right now. So they determined that for you to be able to sample a continuous time and to be able to reconstruct that signal back from its samples, which is important, you have to.
Faster.
Is what?
It has to be twice as fast.
Has to be twice as fast. Yes. Can anybody remember the name of the gentleman?
Sir?
Eh?
Nyquist?
Nyquist and Nyquist was really, yes. Nyquist, I think, really defined it. That's true. But also the third gentleman I'm thinking about, his name has just slipped me, but certainly Nyquist. Yes, sir. The name of the sampling frequency that you have to observe is Nyquist. So and Shannon. Shannon was the third person. So Nyquist and Shannon certainly did a lot of research into it, and Nyquist, I think, was the first person who determined that you had to sample at twice the highest frequency in your signal, right? So the Nyquist frequency then is twice the highest frequency, Fs equal to F max, or however you want to define it. Right, now, that's all very well, but certainly in the earlier days, it would be easier to understand because you could generate your sampling period by having a rotating switch that closed every one rotation, for example. So if that switch there was rotating, if it was built on a rotating commutator, then you would make contact with your input signal and sample your input signal once every rotation or once every 2 pi, angular rotations of your commutator. In other words, the commutator going around one time rotates through 2 pi radians. So now we can basically think of our sampling frequency in terms of pi, because each time it goes through 2 pi radians and you take a sample. So we then now have got our frequency samples in terms of radians per sample, right? And it was discovered then that if your sampling frequency was less than twice your highest frequency in your signal, then you would get something called aliasing. In other words, you would begin to see frequencies that weren't there originally. They would be appearing in the output of your sampler. I have a little lab which you can do on your computer, which is may help to explain. I'll send it. It's a digital communication lab, but I will send it out, and if those who would like to try it, it's not hard, and you don't have to submit a report. You can demonstrate aliasing. Anyway, my point is that we therefore are going to, in DSP then, our signal processor does not know what the real world frequency is. It only knows what the frequency is in terms of the sampling frequency. So every every frequency that is going to be dealt with by your signal processor is going to be in relationship to 2 pi, because 2 pi represents 2 times the sampling, 2 times your highest frequency. Your sampling frequency is 2 pi, your highest frequency, then radians. And anywhere between 0 and pi radians, those are the frequencies that you can allow in your input signal. The DSP then has no idea what the outside world frequency is. The DSP is going to do all its calculations based on this pi, on the radians per sample. Right? So it means a lot of things. But amongst other things, it means that if you designed a signal processor and your sampling frequency, let us say, was 20 kilohertz, that means you could handle all frequencies up to 10 kilohertz. Then if that sampling frequency was changed, that will throw out your DSP altogether, because your DSP will still be working on the basis, the algorithms will be working on the basis that your sampling frequency was 20 kilohertz, right? But it has changed. So things will change in the DSP, and we'll just look at that again a little later on. But it's just one of the interesting things. So all your frequencies are going to be normalized, right? And we've already encountered what normalization means in terms of amplitude. Here now we're dealing with normalization in terms of frequency. So 2 pi will represent your sampling frequency. Pi will represent the highest frequency that is allowed in your input signal. Right, so that's why we see then our frequency plot is going to go from 0 to pi radians per sample. And we will see this again, if we were to continue looking between pi and 2 pi radians, we might be surprised to see that there is something there. In actual fact, what we will find generally is there is going to be a mirror image of any signal that is shown between 0 and pi is going to be mirrored between pi and 2 pi. We'll look at that again as we go along. So I hope I've made it a little bit more clear. As I say, it was off the cuff, and it's a bit difficult to follow without diagrams and so on. But we will now be looking at what we call a digital frequency. So how do we actually determine a digital frequency? All right, I'm going to take a break, and then we'll come back in 10 minutes, and I will bring up the chalkboard on this, and I'll try and explain a bit more in terms of that. So see you in about 10 minutes then. I'm going to stop this recording now. Right, so we will have a recording just for all of that went along. Right, so in 10 minutes.
Yes, sir, please.
I'll start and very quickly go back over it again. Digital frequency. It's common then to express conventional frequency as a fraction of the sampling frequency when you're talking about digital signal processing. Or digital frequency, as shown here in terms of cycles per sample, is always going to be less than about 0.5, because your frequency of interest, F, shown here, should always be less than half of your sampling frequency. Hence, your digital frequency is going to be something, as I said, less than 0.5. Now, in terms of DSP, it is even more preferable to express your digital frequency in terms of radians per sample. And this is given the symbol omega, capital omega. And where omega then is equal to 2 pi times the frequency of interest, F, over Fs. And the units are radians per sample. So if we go back, if we're going back, we'll see that it is referred to by MATLAB as normalized frequency in terms of radians per sample times pi. Okay, so right. So here you're going to have, in terms of your digital frequency, you're going to have 2 pi times a number which is always going to be less than 0.5. So highest possible value should be 0.5 here, so 2 times 0.5. So generally that's why MATLAB normalizes it to pi radians per sample. That is the highest frequency that you should be handling by your DSP. So in the graph there, it showed it normalized to pi radians per sample. So it's very simple. So let's look at an example then. If a 5 Hertz sinusoid is sampled at 25 Hertz, what is its digital frequency? Right, so in terms of Hertz cycles per sample, or Hertz per sample then, you would just simply divide 5 by 25, and that would give you 1 over 5 or 0.2. However, we will tend to use radians per sample, so therefore our omega, our digital frequency in radians per sample, is going to be 2 times pi times 5 over 25, which is 1.257 radians per sample. Right, so having seen this now, we realize that if we don't know our sampling frequency, right, so if we can, if we don't know what our sampling frequency is and our DSP doesn't know, we're going to find that we'll simply be designing our DSP in terms of what the cutoff frequencies are, or whatever we want it to be. Right. So if we had a sampling frequency of, say, 5,000 Hertz, and we were interested in in what is the digital frequency of a 1000 hertz signal, then we know that it would be 1/5, so it would simply be the same thing. So let us look back at our previous filter, the one with quarter, half, and quarter coefficients. And I'm going to give you give you this little problem, and it'd be nice if we could look back and just look at that the graph. But the problem is, if the cutoff frequency in the previous low-pass filter, let us say it was 0.27 radians per sample, and you needed a filter to have a cutoff frequency of 3.4 kilohertz, can you work out what the sampling frequency needs? What would the sampling frequency need to be? So I'll just go back. Remember, we said our cutoff frequency was going to be 0.27 radians per sample, right? So going back up here, we saw that it would be somewhere about here. That would give us, this is 0.25, 0.26, 0.27, somewhere about here. We would want to have our cutoff frequency being about there. Now, it may not be 3 dB down. In fact, this is actually 3 dB down. But we're just using this as an illustration. So hopefully, conceptually, you can understand what we're saying here. That we want a cutoff frequency somewhere around there, which is 0.27. I didn't include, I just said 0.27. So in fact, it isn't this is times pi, but I did not put 0.27 down here. So let us go back and let us say it is 0.27 pi radians per sample. So this is our, so there should be a pi there. Then we insert pi. All right, and then we from currents. All right, so our cutoff frequency needed to be 0.27 pi radians per sample. All right, and you need, well, it was 0.27 pi radians per sample. That's the cutoff frequency, and you need the filter to have a real world cutoff frequency of 3.4 kilohertz. What sampling frequency would you need? All right, so I'll give you a few minutes to try that. Anybody who has, as soon as you have an answer, you can, I don't see, where's the chat? So, okay, here's the chat. All right, so you can, as soon as you have the answer, you can put it on in the chat room there.
Sir, would you just multiply it?
Just multiply it by what? You don't mean multiply 0.27 by pi. I don't think that would give you the frequency. Because pi is just 3.142.
Yeah, no, sir. The 3.4K by the 0.27 pi, if I'm understanding.
Well, let me see. I didn't work it out yet. Let me just see. I won't say the procedure that I would use yet. Let me just use the procedure that I would use and see what I get. All right. So Hmm.
Mm.
Nobody come up with an answer yet?
Sorry.
Yeah.
What does it? The 3.4 kilohertz. That would be the Could that be equal to like like for example a sinusoid in that case? Because I think I'm probably mixing it up.
All right. No, the 3.4 kilohertz. Well, it's just a frequency, but that's the frequency you want to cut off your signal at. It should be at 3 dB. Your signal should be attenuated 3 dB. But the cutoff frequency in the filter that we designed, we are just saying is 0.27 pi. That's the cutoff frequency in the DSP. The cutoff frequency in the real world is 3,400 hertz, right? So 0.27 pi equal 3,400 hertz. Okay, so should I say more? And what is the sampling frequency? The sampling frequency is 2 pi. So what do you need to do then? You make pi the subject of that. So you have 3,400 hertz equal 0.27 pi. Therefore, you can find out what pi is and then multiply by 2 to get your 2 pi, which is sampling frequency. So, anybody come up with that?
Sir, can you repeat that, please?
Okay. The cutoff frequency in the filter is 0.27 pi, right? Radians per sample. Right? So, in the real world, that is equal to 3.4 kilohertz, right? So you should just have to divide 3,400 hertz by 0.27, and that will tell you what pi is. But your sampling frequency is 2 pi.
Oh, okay.
You're following?
So it's 25 2.185 kilohertz, 25.1. No, sir.
You didn't get it? You got it?
25.185 kilohertz.
Yeah, yes. It looked like, yes. I think it's that, yeah.
Sir, I did it, sir, but I just wasn't sure. I wasn't sure if what I did was correct. That's why I asked again about the 3.4. But you're saying that they are related because the 0.27 pi rads per sample. That is the time, the frequency of the DSP, right?
Right.
And it is equivalent in real time, in real world time, or real frequency. It is equivalent to the 3.4 kilohertz.
Right. Yeah.
Okay, sir. I made that assumption, but I wasn't sure. That's why I asked again about the 3.4.
Right. Or, I mean...
Can you repeat the answer you get, my boss?
25.185 kilohertz.
185. Oh, yeah. Yeah. I think I rounded 184, yeah. 592 times, yeah. Anyway, Yeah, right. Because if you think about it, right, pi, remember pi is just a number again. So you could have divided 3,400 by pi, and you would get you get that in terms of cycles per sample. So, or it would be 0.27 cycles per sample. And then you would, or you would divide it by, if you, yeah. No, not a good method. Anyway, you could divide 3,400 by 0.27 and then multiply that by 2 to get your 2 pi. But that's a bit confusing. Best to just to do it the way we had said. Not converting to cycles per sample. Yeah, well, that is it. So, the whole discrete time to continuous time conversion, we don't really need to know. We don't really need to know what is going on in there. We don't necessarily need to know about Nyquist theorem and all that kind of thing. We only need to be able to convert from, and it's not even really meant to be part of the DSP syllabus, but it has crept in over the years. But I'm trying to avoid going into a whole lot of detail because time is on the short side now. So we really only need to be able to appreciate Nyquist theorem, that we must have our sampling frequency must be at least 2 times the highest frequency we're going to process. That we will also have to realize that whether or not we're sampling at Nyquist frequency or not, in general, an alias would appear between pi and 2 pi as we go around that unit circle. So remember our circle is 2 pi radians around, right? So as we go around that circle, the segment, I'm not using the right word, but the segment then between 0 and pi is the one in which we actually see our signal that we are processing. What happens between pi and 2 pi is that there is usually a mirror. There's always a mirror image when we go around there. We'll see it as we go along. But for all intents and purposes, what we will mainly need to be able to do is to convert between sampling frequency, which is 2 pi, and the frequencies that we are concerned with. So if our sampling frequency, for example, was 2,000 samples per second, then 2 pi is going to be 2,000 samples per second. Therefore, if we want to work on a frequency which is, say, 500 hertz, then it is going to be 2 pi, 2,000 over 5, did I say? So that is 4, and then it is going to be 2 pi over 4, which is pi over 2. So our signal is going to be, we are going to be thinking pi over 2. We're not going to be thinking 500 hertz because 500 hertz doesn't exist in the DSP. But pi over 2 exists as 500 hertz when the sampling frequency is 2000 hertz. I know I'm getting confusing, so I'm going to stop here. But a little practice and it will all come together. Right. No, your just before you go, your lab, which I thought was available to you. I didn't tick something that said publish or whatever, so it wasn't available. So I did that yesterday, I think. All right. So it is quite. I hope you find it an enjoyable lab. You're going to take your voice now, and you're going to introduce echo into your voice and reverberation. So they're actually two different things that you do, you know. So I hope you will enjoy it, and I hope it won't take you too long. I've given you about 2 weeks to do it in. So with all that said, I will wrap up now. And any question or comments or anything?
Hello. Excuse me, sir.
Yes.
Hello.
Yeah. Oh, sorry. Hold on. Yeah, can you hear me? You're not hearing me?
Yes, sir, we're here.
Oh, okay. Yes, go ahead. No question?
Sir.
Go ahead.
Do you have any tutorial sheets or anything like that we can?
Right. I have some stuff. I will email it out to you. I try and do that.
Email, sir.
By tomorrow or so, maybe this evening. I don't know. I'll go and look and I should be able to email it out in a half hour or so.
Yes, sir. Sir, if you have any recommended text, that would be good.
Yeah, something that can simplify the theory that we have, sir.
All right. Yeah, it's probably not simplify it, but it will explain it better than I am explaining it, and it will provide you with an alternative explanation, which hopefully will be useful. Right. I mean, the recommended text for the course is by Orphanides. I don't know which one. It's a red covered book. And even the last time I heard that people were able to download it in soft copy. I have a hard copy, and Orphanides is quite good. I myself like a textbook by I think it's Sanjit Mitra. I think he must be Indian, because he explains things in very, very straightforward language. DSP can be a bit
Convoluted.
Imposing and convoluted. Yes. It's not really, once you get to know it, but it can be a bit imposing because of all the symbols that are required, in DSP and all that. So, I mean, I'm trying to keep things to a minimum where the symbols are concerned. In actual operation and also, it is dead simple. I mean, it is, as I mentioned before, very, very simple. It's how you achieve certain things, which a lot of things are quite clever. And who knew that mathematically, because a laptop cannot do integration, not unless they're going to do numerical integration and so on. But it can do summation very, very well. So DSP chips, they do three things. They add, multiply, and delay. And that's all they do. And everything else is derived from those. So yeah, Mitra, I don't know. What I have is quite an old copy of his now. And what I like about Mitra also is that he does give examples using MATLAB. And so you can, if you want to see things and, you can type in the command. You don't have to try and develop the code yourself. But, go ahead.
Could you repeat the name of the author of the book that you spoke about first?
The first one is he's Orphanides, ORFINIDIS, I think. ORFANIDIS. And just type it in. His first name is Sophocles, like the Greek. He's probably Greek. I don't know, but I am aware that people have been able to download free copies of his book and so on. It's quite good. A lot of stuff.
Sir, and do you remember the title, sir, of that book?
Oh, it's my copy is up at YouTube. Isn't it? It's in there. Yeah, I couldn't find there. In Canvas, you haven't looked at the introductory part of Canvas. I have recommended reference material.
Okay, sir. I will look.
Yeah. The actual module textbook from ever since is and I put processing by Oppenheim and Schaefer, which is supposed to be the Bible of digital signal processing. And those two there are the gods of digital signal processing. But it's a bit more difficult to read and follow. Orphanides is really quite readable. His book is called A Computer-Based Approach to Digital. I like it because of that. And I can send out a soft copy of Schaum's outline, but Schaum's outline not a great book, but it can help,
Yes, sir.
I'll email out that copy there. I hope I have it on my computer here. Well, this is at home. I think you can download Schaum's quite easily off the internet. So, all right, anything else? All right, well, I'm wrapping up then. I will try and remember all the things I've promised to send to you, and I'm going to work on them now. So have a good evening, and see you next week then.
All right, sir.
Okay, all right.
Sir,
Yes.
are all of the slides on Canvas?
Right. What I'll do, I'm going to put the slides in PDF form and put them on. And yes, I'm going to put them on. I think I can just put them straight into the sections where they are. So I'm going to try and do all of that. I have so much work trying to do. But yes, I'll put the slides on.
Yes, sir, that would be good. Thank you.
Okay then.